Today, guys, we're going to take a short foray into differential equations. The title of this section, 3.8, is Natural Growth and Decay. Now, the reason we do this is naturally growing things, like populations, for example, and decaying things, such as, again, populations, if they're all dying out, or radioactivity, they satisfy a certain differential equation, and that is that the rate of change of your problem is proportional to the size of the function value. So what this says here, if you're talking about a population of rabbits or bacteria or people or something, then the rate of change, the rate of growth of that population is proportional to the size of the population. If there's more bacteria splitting off and creating more bacteria, then you're going to have a larger increase than if you only had, 2. Now, I'm going to satisfy my own mathematical nature here. This is a differential equation which is classified as separable, meaning I can separate the variables. Now, we're not going to have to deal with any differential equations or solve any differential equations in this class, but I'm going to do it just so you have an idea of what lies ahead in the far future if you decide to stay with applied mathematics. So what I do for these is, since this is separable, what I like to do is group together all of the like variables. This k here is a constant, and I'm going to call it the rate constant. And naturally, it controls a great deal of the problems that we're going to be having. So I'll separate these variables. I'll have 1 over y times dy equals k times dt. And the way I solve these kinds of differential equations is I just use integration. And it turns out, this first one, the integral of 1 over y dy, this is equal to the natural log of y. And this is equal to, this other integral is equal to t times k. And what always happens when I have integrals is I have this extra constant of integration that comes out at the end. We're going to be doing integrals by the end of this class, so I'm going to say it now. Never forget the plus c. I'll raise both sides to the power of e, so I'll have e to the natural log the absolute value of y. Those cancel, so I'm left with absolute value of y equals, I'm going to change the order of this. I'll write e to the k times t plus c. That's up in the exponent. But using exponential properties, this is e to the c. Or, since c is a constant, this is just some new big constant. So if I take this problem and try to plug in t equal to 0, I'll have y of 0 equals c times e to the power of 0, which is equal to c. And I'll write this as y sub 0. So if I rewrite my equation, or my formula, I could say, I'm going to get the absolute value of y equals the absolute value of y sub 0 times e to the kt. Now, since this is a non-negative number, it basically says that y and y0 are not going to be different in sign. So, hand wave a little bit, but I get the final equation, y equals y0 times e to the kt. And this formula here is going to be the governing equation for pretty much literally every problem in this section. This right here is a solution to the differential equation for natural growth and decay. What we'll notice here, if the rate constant is positive we will have growth. And if k, the rate constant, is less than 0, we have decay. If k is equal to 0, then, well, I'm not changing anything at all. So for our first example, we do a standard population growth problem. Let me write it really fast. So my situation is, a bacterium is introduced into a favorable medium. The initial population of the colony is 12 whole bacteria, and after 3 hours the population of the colony has risen to 200. And I want to know, how long is it going to take until the population reaches over 1,000? For the specific letters I'm going to use for this problem, I'm going to use P for population, and I'm going to have the initial population times e to the kt. Now my problem has given me enough information to find out what the rate constant is, because I know the initial population is 12. But I need my k in order to do anything with my function. So I know that after 3 hours the population has risen to 200, which means P of 3 is equal to 200. But also, P of 3 is equal to 12 times e to the k times 3. Which means these two numbers have to be equal to each other. So I have 200 equal to 12e to the 3k. Notice k is my only variable in this problem, so what I'll be able to do is solve for k. So first I'll need to divide both sides by 12 to get 200 over 12. I can simplify this a little. 100 over 6, 50 divided by 3. And this is equal to e to the 3k. Now I have an exponent, and you may know by now that I don't like exponents, so I'm going to take the natural log of both sides. Get natural log of 50 divided by 3 equals 3k, because the natural log and the e will cancel, leaving me with k equal to the natural log of 50 over 3 all over 3. I found my k. This is my rate constant. This is probably going to be the first step of every problem we ever have to do with this section. So what I'm going to do is I'm just going to rewrite my function now that I know what my k is, and then try to address my problem. The question posed is how long until the population of the colony surpasses 1,000. So I'm just going to find out how long it takes to get to 1,000. So I'll have 1,000 equals 12 e to the natural log of 50 divided by 3 over 3 times t. And now I want to solve for my time t. So I'll have 1,000 divided by 12, which is 500 over 6, which is 250 over 3. E to the natural log 50 over 3 t. Take natural log of both sides again. I'll have the natural log of 250 divided by 3 equal to the natural log of 50 divided by 3 times t, which means my t is this lovely number, now I'm not going to be able to do anything with this number without a calculator, so I'm just going to leave this like it is. I'm going to add units. These are in hours. If I had a working calculator, I'd probably be able to take the next step, but this is as far as we're going to need to go. Another common example is calculating problems involving radioactive decay. It turns out that the rate at which a substance decays is proportional to the amount of substance which remains. So let me write out a prompt really fast. So the situation we have is a newly discovered substance, Clemsonite, has a half-life of 11 weeks, or 77 days. Now, if a sample initially contains 5 grams, how long will it take to decay down to 2 grams? So first, the half-life, commonly lambda, is 77 days, and this is the time it takes for the substance to reduce by half. So the letters I'm going to use for this problem are m for mass. This is equal to m sub 0 e to the kt. Now, my half-life is 77 days, which means that 1/2 of the initial is what happens when I plug in 77 days. Or 1/2 is equal to e to the 77k, which actually helps me solve for the k value. My natural log of 1/2 will be 77k, or k is equal to natural log of 1/2 over 77. Now that I have my k value, I can rewrite my function, so I'll have m equals, my initial value is 5 grams, e to the natural log of 1/2 over 77 times t. Now you notice the first time I didn't actually use the number 5 for my m sub 0, and that's because often for these growth and decay problems, the initial value doesn't matter quite so much as the ratio by which it has grown or decayed. Now to address my question, I want to find out how long it takes to decay to 2 grams. So I'll set my value here equal to 2. I want 2 grams. I want to solve for the t. That gives me 2 grams left. And this is going to be slightly more than 77 days, whatever it is. So I'll have 2/5 equals e to the natural log of 1/2 over 77 times t, or the natural log of 2/5 equals natural log of 1/2 over 77 times t. So I get t equal to 77 natural log of 2/5 all over natural log of 1/2. And this is in days, because I used 77 days to plug in. Now, just so that I can do something different from the first example, I'm going to ask essentially the other type of question: how much remains after 100 days? But for this, all I need to do, since I've already done the work to find my k, is just plug 100 into my function, which is not a terrible prospect. So m after 100 days would be equal to 5 times e to the natural log of 1/2 over 77 multiplied by 100. But again, without the aid of a calculator, I can't do much of anything with that by hand. And this will be in grams. The third kind of example we have out of this problem is one of my personal favorites, Newton's law of cooling, or heating. Now, these are a little bit different because the rate of change of the temperature of an object is not necessarily proportional to the temperature of the object, but it's actually proportional to the difference of the temperature and its environment. Because the greater the difference, the greater the flow of heat, or the greater the rate of heat transfer. But if it's a very small difference, then the heat will not transfer very quickly because there's not as great of a pull. So the way these work is I have y equal to the temperature of the object minus the temperature of the environment. It's acceptable to write these the other way around. You just have to be consistent with when you do your problems. So if I define the y variable as such, then y will follow the equation, and hence the differential equation, y sub 0 e to the kt. So an example I have for that is, really fast, we'll suppose a bowl of chilled monkey brains, delicacy, initially at 34 degrees Fahrenheit, is set out into the dining hall of the Temple of Doom, which has an ambient temperature of 74 degrees. Because of all the fire. It's really warm in there. Now, after 15 minutes, the dish has warmed to a temperature of 47 degrees Fahrenheit. And I want to know what is the temperature of the dish after 40 minutes. So for our setup, always remember that the variable we're using is the temperature of the object, so I'll call it temperature of the bowl, minus the temperature of the surroundings, so I'll call this the temperature of the room. So my initial value for y is the initial temperature of the bowl, 34, minus the initial, constant temperature of the room, 74. And this is equal to negative 40. The book might tell you that you're not allowed to have negative values, but guess what? I'm smarter than the book. Now, this means we have a prototype equation, y equal to negative 40 e to the kt. Now our first task, as always, is going to try to find out what this k is. Now, it tells me that after 15 minutes the bowl has warmed to 47 degrees. I'm going to use that. Which means y after 15 minutes the bowl has warmed to 47 degrees. So this is 47 minus 74. Don't forget this. And if I take this difference, I get negative 27. Which means I have negative 27 equals negative 40 e to the k times 15. Or, if I divide everywhere by negative 40, I get 27 over 40, with no negatives because they cancel, equals e to the k times 15. That step right there is exactly why we're allowed to have negative values for the y's. So this means the natural log of 27 over 40 is equal to 15 times k, or my k is now equal to the natural log of 27 over 40 all over 15. Now that I have my k value, I can fill out my equation. I'll have y equals negative 40 times e to the natural log of 27 over 40 over 15 times t. And what I wanted to know for this problem is what is the temperature of the bowl of Minky Brains after 40 minutes. So I'm going to find out what y of 40 is. This is equal to negative 40 e to the natural log of 27 over 40 over 15 times 40. Now I'm just going to leave it like that. But remember that the y value is equal to the bowl minus the room. So if I want the temperature of the bowl, I have to add the temperature of the room to both sides. It's the temperature of the room plus y of 40, which means after 40 minutes, the temperature of the bowl is equal to 74 plus y of 40. So this is negative 40 e to the natural log of 27 over 40 over 15 times 40. And that is degrees Fahrenheit. For these Newton's law of cooling and heating problems, you can use the same function for both. What's just going to change is whether you have positive or negative numbers, depending on how you set up your y. But you always want to be aware that your y is equal to a difference of the object you're interested in and the room. So if I wanted to say, find out how long it takes to get to a certain temperature, I have to remember to plug that temperature into the function, into the little mini formula for the y's, in order to find out what my appropriate y value is going to be for use with my general formula. To wrap up, our last topic for this section is money. Now, it's possible from pre-calculus or some other class we had learned about interest rates. That after I apply interest, the amount of money I have is equal to my capital A sub 0, or my initial amount, times 1 plus r over n to the n times t. For here r is the interest rate in decimal form, and n is the number of times we compound the interest. So if I had a 4% interest rate which compounded monthly, I would have a equal to my initial times 1 plus 0.04, If it's monthly, that's 12 times per year times 12 times t. And I always calculate these where t is in years. But what we're interested in is, in calculus, we like things to happen in a continuous manner. We're doing continuous mathematics instead of discrete mathematics, whatever that means. So as the number of compounds increases, I'm going to have larger n values. So the natural question is, what happens if I compound infinitely many times? And for that means we apply a limit. And the compounding part is this guy right here. So the question is, what is the limit as n goes to infinity of 1 plus r over n times nt? Well, it turns out we do a little change of variable for this problem. If m is equal to n divided by r, because the rate is not changing but the n is, then m goes to infinity as n goes to infinity, and I can rewrite my limit as m goes to infinity. I'll have 1 plus 1 over m times rmt, because m is equal to n divided by r, that means n is equal to r times m. Or if I rewrite this again, I have the limit as m goes to infinity of 1 plus 1 over m to the m power, all of that raised to the RT. This is one of those limit laws that I can apply. Well, as it turns out, this limit right down here, this is one of the possible definitions for the number e. This is equal to, or this guy right here is equal to e, which is about 2.7182818280459. So this is equal to e to the RT. So if I want to compound continuously, or if I want to compound infinitely many times for my money, I have a new formula. I have a equals to a0 e to the RT, where the r here is still your interest rate. But you'll notice that this is exactly like the formulas I've been using for the rest of this section. So I'm not going to do one of these examples because this is going to work exactly like the population growth problem, assuming I want to gain money and not lose it. We have only 2 sections left this week before the test on Friday. I'll do my best to try to get both of those up by the end of tomorrow, on Wednesday. There will also be a second quiz given out on Wednesday for you to work on some of these problems in a different setting to prepare for the exam.